Okay, so today we're going to talk again about real-time operating systems. This time uh, we're going to talk about how you would implement your own real-time kernel on the AVR. Now, we do have an assignment, and in that assignment you will take a real-time kernel, and after this lecture you should be able to understand what all these procedures are doing for you and what is happening there. Now, that will then also allow you to be able to implement your own schedule, your own policy. Alright, so let's again let's go quickly through the following bunch of slides, because it's kind of a repeat of what I've talked about earlier in yet a different way. But say we have these types of tasks. We have periodic tasks, like an ADC sensor that you want to read every 100 milliseconds. So the worst case execution time is less than the period t, of course, otherwise you cannot meet that deadline. And generally the deadline of the invocation time, so at k minus 1 times t, you say, okay, I want to start sensing that ADC sensor again. I want to find out what it says. Then the deadline for this is then considered to be a period t later, so at k times t. Aperiodic tasks are invoked just once, say initialization sequence. An aperiodic task has a defined worst case execution time and a deadline relative to the invocation time. Soft aperiodic tasks, that's how we call them, they do not have any deadline constraints. Then we have sporadic tasks. They can arrive at any arbitrary point in time and are constrained with a minimum inter-arrival time, say 2 consecutive invocations or at least t time units apart, where t is the minimum inter-arrival time, and this could, for example, be the handler for your keyboard, where the human essentially creates that minimum, the limit of the human's typing speed, pressing the keyboard, actually leads to such a type of minimum inter-arrival time. Alright, so we talked about the OS kernel before. It consists of scheduling, resource management, I/O services, and so forth. The operating systems such as Linux, they employ kernels that allow users to access to the computer resources seemingly simultaneously, so that is the multitasking that we talked about earlier. And along with other jobs, the kernel takes care of CPU time that is shared among all these different tasks. And it's sort of, it's a pseudo-parallelism that we observe, because in reality, of course, all these tasks are context switched in and out and are executed, from back, in slots in sequential sense. We have seen this particular picture before. So here we see, right, so you have a bunch of tasks, and you, for example, have this type of scheduling. So the scheduling policy determines which task should be run next. So let's talk about this slide. Here, why do we need a real-time kernel? Well, a simple example here where task 1 needs to run strictly 1 second, and assume the code shown are running on your AVR. So here we are, code 1 and code 2. The question is, do they meet the timing constraints? And the RTOS can react to various unpredictable events and at runtime, and better manage the resources to meet those deadlines. And in this example, we notice that there are these executions, but if it starts too late, you will have a missed deadline. And for code 2 here, you would have the missed deadline over here. So you need to be very careful. So we need to understand what the real-time operating system must do, and we first understand again, what is this execution context? We talked about it before. It consists of the program counter, the status register of your ADMAKER processor that has all the settings for in global interrupt enable and that kind of stuff. we have the processor's general purpose registers, 32 of those in total, and a stack pointer that points here at the stack where a piece, say a code for a procedure is stored for a task. So if we do context switching, what do we want to do? Well, we saw this slide already earlier, so I'll just very quickly go over it, but what we want to do is obviously to restore all the register's content plus where you are exactly in the program memory with respect to the program counter, and of course the stack pointer should be set back to its original spot. So in other words, you want to restore the CPU exactly in its original state. And why? Well, you could have already loaded arguments in the registers, but you have not yet performed the add instruction on those registers. So you need to be exactly precise about restoring the state upon a context switch. So let's talk about core concepts for implementing this RTOS kernel. We've already seen that we need what we call the RTOS tick, like a timer that's going to interrupt or gives a timer interrupt to the real-time operating system effectively, that can then have a look. Am I going to keep on going with my current task, or should I context switch it out? And do I need to do some management of some kind, and so on? So the kernel keeps track of the real time using a timer ISR and maintaining a software counter that counts a number of ISR invocations, or so-called ticks. Now, the tick interval can be configured, and that allows the kernel to measure the real time down to the resolution of a tick interval. So clearly, well, we saw this diagram earlier where we said, well, you can be ready as a task. You may be blocked because your resources that you need at that particular moment are not available. They're used by another task. And so you will have the ISR implement when upon each tick the timer ISR will have a look whether blocked task can be moved to the ready queue, and then of course also figure out whether after the ISR you should jump back to the interrupted task and continue its execution, or maybe suspend the interrupted task and start running a different task by scheduling by context switching. And the scheduling policy really decides which task is to be run next. Alright, so jumping in and out of an ISR. Well, return a control to the same task. So let's have a look at that. Well, first of all, upon an RTOS tick, so a timer 1 compare A interrupt, right? That's how we will implement it. The CPU program counter jumps to the ISR code. So here we have the ISR code. And what's going on? So the compiler needs to ensure that every processor register that gets modified in the ISR code is restored to its original value when the ISR exits. And that is, and look what's going on here. We here save the context of the interrupted task, a limited set of registers actually, and this is effectively the additional code that is generated by the compiler. You don't do that yourself, right? You just write the code here, but effectively the compiler adds in these instructions that save the context of the interrupted task, and then at exit the compiler has added also code to restore the context of the interrupted task. So so what is it doing? So prior to the ISR execution, it saves only those register values that are going to be used in the ISR code, because all the other register values, they will be left untouched. So that means that at the beginning and at the end they have not changed, and so when you so you do not need to additionally save those and restore those because they didn't change. After the ISR's execution, it restores those registers that potentially have been changed in this code, and that is what you will do here. So you pop those registers from the stack, and you will put them into the right registers. Look, it's in reverse order. You've been pushing the value of R1 on the stack, next R0, next I think you do a clear of next you put in the status register in R0, then you push that value onto the stack, then you do something here with R1, and then you push these registers out, and in reverse order you take all of this out and so forth. Alright, so we also see here an RETI instruction, a return instruction, and that gives the control back to the interrupted task. Effectively, this will pop the program counter off the stack, and that will then now point at the right spot in the program memory where the interrupted task had stopped and now is ready to continue execution. Alright, so if you have a different task over here, so then we really want to, because we go to a different task, then in that case, the original task that is going to be context switched out has potentially all the registers can potentially be modified, and not necessarily inside the actual ISR code, but definitely when it context switches in this other task, and this other task is going to change all these register content. So what does that mean? I really want to save the entire context of all registers, right? Now, how can I do this? Well, the idea is that we, the user needs to explicitly write code for saving, restoring the entire context. And this means that the compiler's auto-generated code is unnecessary. And for that reason, we put in the ISR naked argument into the ISR that now tells the compiler not to generate any of this additional code that we had at the earlier slide. We are going to do it ourselves. So the user explicitly writes this code to save, restore the entire context, and again with the return instruction at the end to go back. So here we have that code, and we're going to discuss that into more detail a little bit later. So what about this application stack? So that's important, because when we talk about popping and pushing, we're talking about manipulating the stack effectively. So here we have a slide on that. So say we have two tasks, they each have a stack pointer, and when we look at that pointer, it points effectively at the context of that task. So all the register values, the status register, and also the program counter. So the stack of the currently running task is pointed by the processor stack pointer register. Alright, so that is the register of the processor, and any push operation writes data to the stack, so it pushes it on top of it, or any pop operation reads the data from the stack, and then the pointer will decrement. So while jumping into a function or ISR, the address of the next instruction to be executed is pushed to the stack automatically. So, and this address is also called the return address or the program counter. So that's done automatically. That is what your hardware is doing. And after the execution of the function, the return instruction pops the return address from the stack and jumps to this address to execute the code. So that's what this RETI is doing for you at the very end of the code that you have seen at the earlier slide. Over here at the very bottom. Okay. So let's continue and have a look at a more detailed example of a context switch. So what do we see here? So we see here all the general purpose registers, the status register, the program counter, the stack pointer, and of course the program counter is pointing at the task A code. So here we have all those assembly instructions, right, and so on. So this is prior to the RTOS tick interrupt. And now that it does occur, we are actually going to, go towards another spot. Wait a minute, what are we doing here? Just making sure I'm correct. Right, so we have the task A code. Then we're going down into the stack. We see the program counter. And the interrupt is executing. What does it what does it do? It actually starts to push the PC on a stack. So the program counter of A, where it is, right, is actually going to be pushed onto the stack automatically. That's what happens when the ISR occurs. And after that, we want to put on the whole context. So what is that? Well, that is going to be your registers, R0, R1 up to R31, plus the status register. And this is the context that you need to separately code up now. And that we are going to do in what we call the port save context functionality. So we'll talk about it in a moment. Now, the kernel is going to store a copy of the stack pointer for each stack. So it knows where to find for each task, task A, task B here, the context. So if you're going to switch to a task B, then it will now load, it will have a look at this table and will then look at the stack to find the task B's context and then go from there. So let's see. So for example, in this particular case, the task B stack pointer is retrieved. It's pushed into here, it's loaded, and now this will point at this particular spot, and here we see the whole context of task B. So what are you going to do? You're actually going to load all that information. So you restore task B's context by loading all that information from the stack into the registers and the status register. And then we are here. Then we use the RETI instruction, and that instruction will actually push this PCI, this program counter, into the program counter here. So that's what we do now. So there it is. And now it points at the task B code where you had left off, and the whole context is the same. So now you start working on that piece of code. Now you see that this task B code may manipulate all those registers, and that's why we had to really make sure to save all the registers and save the whole context. Now, if you would have returned to task A again, as you had seen in the earlier slide, then in that case, well, you only cared about what the interrupt itself was manipulating, which registers were then will be changed in the ISR's code itself. And therefore, we only had to save the partial context, which is automatically done by the compiler, and we do not need to worry about that. Alright, so here we are. So let's see how this return instruction is working a little bit more in detail. So here we have the task A stack, the task B stack, right? So we have a stack pointer that points over here. We have the task A is executing right at this particular moment in time. And we have loaded everything of task A, the context, into the CPU, you can say. On a context switch, you start writing all kinds of stuff here, and then you jump to the stack B pointer so that you can start reading all of this. So let's have a look at this. So the CPU always executes the code pointed by its program counter. So here it is, and one can redirect the program flow to any arbitrary location by manipulating this PC register, but you're not allowed to do it just like that. So let's have a look. You cannot directly modify this, and one can load the PC only with an arbitrary value through the return instruction. So the return instruction, the RET or the RETI. So that is how you will manipulate the program flow. Alright, so let's have a look. So when called, the return instruction expects that the stack pointer points to the value to be loaded in the PC. So when you have context switch in all of the context of task B, then at the very end the stack pointer will be pointing over here, right? So now the stack pointer points to the value to be loaded in the PC. And now if you are calling the RET or the RETI, function, then it will put the value that the stack pointer is pointing at into the PC. So that is how the RTOS kernel uses this method to switch the program flow among the different tasks. Alright. So that's what's happening here. So we have before so on a context switch, we're going to load all the context onto the task A stack, and then we're going to switch we're going to, the stack pointer will be redirected to the stack of B. You're going to read in all of the context of stack B, and now on the return instruction the PC is loaded in here, and you point at the right spot in task B code and you resume execution of that task B. Alright, so what about the idle task? So actually that's kind of interesting. It's a little thing that we always need to take care of. Periodic tasks typically they execute for a small amount of time. But it means that the CPU, since it's always running, may not have anything to execute with respect to all the tasks that you have implemented. So it needs to do some idle task. And that's why the RTOS kernel implements its idle task in the system. So if there's nothing to do, you just go and execute this idle task. It's just an infinite loop doing nothing. So the RTOS needs to take care of this as well. So that's what this slide is about, and the rest is exactly the same. So once on an RTOS stick, the RTOS scheduler is deciding that, say, task B needs to be context switched in, well, then at that particular moment, the context switch will happen as we did before, and you will read in the context of task B, and you will go to the program counter that belongs to task B. Alright, so that's sort of explained over here and so forth. Alright, so now we're going to talk about some implementation details. So in the code that you will have in your assignment, you will see all these kinds of structures. So here we have one that says a task control block structure. That's what this means. It has some parameters. What's the period, the next ready time, the stack pointer to indicate where you can find the context of that task, etc., etc. Whether it's running, whether it's even ready, it could be blocked, right? So the operating system may not yet have set the flag for ready for this particular task, and so forth. So anyway, so you define this type, and we have a variable, a global variable, which is the task control block structure. And we're going to also create an array, right? So this is the type that has this structure, And then we have an array with all the elements of this type, meaning that every array element is having such a structure for every single task, right? So that's what we have. So that's why we have here the maximum number of tasks. Plus 1, because we also have an idle task. Alright. So what are the user level functions? Well, we have the initialize kernel, so which you will implement with the tick resolution. There's the register task, so there's a task period. We keep it kind of straightforward and simple. And the task function that you want to execute for it. So here we want to start running the tasks, and the naked attribute tells the compiler not to generate any code to save any context before calling this function. So again, the real-time operating system is taking care of that for us, and we don't need the compiler to add in that type of code. Alright, so what are the kernel's internal functions? So here we have the task increment tick, which is simply the kernel's timer of timer 1 in this particular case. And it also sets the ready flags of the tasks. You want to make sure to move those that are not blocked anymore into the ready state. You pick a task for context switching based on, on the scheduler. And of course you will still have your idle task that you also need to implement. Then we have this particular one, it's a handler that's called automatically upon completion of each instance of the periodic tasks. So that's what we do here. Then we also have a scheduling policy. You may add more policies here, and you probably will do in the assignment. So we have a scheduler of a round robin in this particular case. So what's going to happen here? Well, how do we so how are we going to save the context? So this is effectively a repetition of the earlier slide with the earlier code. Remember that if we now call the timer 1, the RTOS tick, interrupt service routine based off timer 1, then we said we gave it an extra argument called a naked. In other words, the compiler is not adding any extra code for switching out the context. It's not saving anything, and you need to do it yourself. So how do you save the context? That's the first question. And the way to do that is by creating this a piece of code. Here you see a lot of assembly again, and you see a certain order to what is going on here. So let's figure out what's happening here. So on the next slide, it's more detailed. So what's going on?